The whole like North Star vision of like making computers that can do discovery has always kind of been like the holy grail. How do we propose the best experiments, and then how do we learn the right information from those experiments? And those are kind of the two things we've just focused a lot of time on. Let me just nail this real quick. I only came here to play pool.
Ron is a co-founder at Entology, a startup building AI scientists. Their system created the first ever AI-generated research article to be accepted into an A-star conference, the highest bar of scientific work.
All right, hold on. I can't mess this up.
That's pretty good.
That was pretty good, actually.
That's pretty good.
Pretty good. Okay.
Yeah, I'm curious, actually. I know you said you play a little bit of pool. I'm curious where you find the time. Obviously, you, I think, founded a research lab, founded a Sequoia Founders Fund-backed email AI company. Where do you get the time, man?
I don't. I don't get the time. I used to have a lot more hobbies, to be honest. I had a lot of hobbies. I used to be pretty cool. Like I used to skateboard a lot. Used to play in a band. Don't really do any of that anymore, unfortunately. But I've been trying to like get myself like out of the house on weekends.
Yeah.
Like do fun things. I haven't played pool in a while, but yeah, I'm getting back into having hobbies again. It's been a while.
I think it's interesting because you've always been pretty much an academic. Was there like an aha moment when you realized you want to start Entology, or was it kind of like a build-up?
Oh yeah, no, it was actually quite a long build-up. So my current co-founder and I, we ran this nonprofit research group for a while. It was actually like what I spent majority of my undergrad and even after working on. Here, I'm gonna come over here. And then it kind of grew pretty large. We were working with like a bunch of different researchers all around the world. We collaborated with DeepMind, like Microsoft, IBM, like published a bunch of papers. And then during that time, he and I like kind of had this idea of the AI scientist, and it was really driven by him. Like his background was in kind of search methods and kind of how we can use that to maybe build systems that kind of do the scientific method and conduct research. And then it was kind of like everything just kind of clicked. Like we had the background, we had the network, and we started working on it, and now we're here.
Yeah, amazing. And was there like, I guess, a problem statement that you've been kind of following throughout your career that really catalyzed this? Like I know you're very focused on kind of like long horizon agents.
Yeah, so I think AI for science has kind of always been like a North Star of the whole like field, and it's something that was hard to make a lot of progress in for a while. So I did a lot of research in like agents and language models broadly, but it was always, at least in the back of my mind, like the whole like North Star vision of like making computers that can do discovery has always kind of been like the holy grail. And I think I was like really convinced on this. When I was in high school, I used to watch Rich Sutton talk at Stanford a lot. Yeah. And he used to give this presentation. The summary of the talk was like, the purpose of humanity is to like create machines that can problem solve and discover better than we can. And there's a more direct path to solving a lot of difficult problems by just creating intelligence that can solve those problems rather than us having to figure it out. And I think that really resonated with me. Yeah, just having the opportunity to work on that was always it just made sense. Like I just want to work on building systems that do science and discovery, and it just seems like there's not many other kind of large like catalyst problems to work on.
Yeah. And then how does it kind of work at a high level? Like I know, right, an artificial scientist, it kind of mimics the scientific process. How does that work procedurally? Yeah,
totally. So I guess for the system that we had that published some academic papers, that's kind of where we made like a lot of our noise. We had like the first few discoveries that were accepted to some AI conferences. And the way that system works, it was very just mapped to the scientific method in the sense where the system was tasked with doing background research on a problem, proposing improvements based on that background research. It then proposes a set of experiments to test those hypotheses, writes those hypotheses in code, analyzes the results, and then kind of had this closed feedback loop of writing new experiments, learning from those experiments, and then based on the results of the previous set of experiments, informing the next set. So that's kind of what was able to allow it to make like the fine-tuning method that was accepted at the conference. And then our big paper was the state-of-the-art jailbreaking method that the system came up with. And that was the one that was accepted to the main conference of ACL, which became the first time a non-human made discovery had been accepted at a large scientific venue of that size.
Yeah, I think the crazy thing, I was looking into it. So it's, I think, the 20% acceptance rate of getting your paper admitted or something like that. But you were, even beyond that, I think the top 8 or so something percent of papers admitted. And so And what was the input it even took? So you give it a topic and kind of let it run with that?
Yeah, so for the original system that came up with those discoveries, the inputs were a lot more simple. We would basically seed it with the problem and like the existing methods in jailbreaking, right? There were some big benchmarks. The human in the loop was basically like setting up that problem, giving it the benchmark, giving it the ability to run experiments, and then everything from the ideas it came up with to the experiments it ran, it all did autonomously. We ended up cleaning up the final paper. Like I made the figures, fixed the errors and citations, but the actual like meat and potatoes discovery of the system was devised and executed by the system autonomously, which we thought was pretty cool.
Yeah, what was going through your and the team's minds, I guess, when that happened, you got accepted into the conference and everything? What was that moment kind of like for you guys?
Yeah, that was a really exciting moment because, so for context, we ourselves and Sakana AI were the two groups who had work accepted to the workshops of iClear, which was a few months before that. And workshops are more of a, like, I don't want to say low bar, they're definitely a high bar, but it's a lot of the times the community views it as a way to get feedback, before submitting to a larger venue. It's more about like, you get to talk to other researchers that, care about your problem. They get to look at your early work and they get feedback before you submit to like the proceedings or like the big conference. And so we actually got explicit permission from the iClear workshop to fly out and present the work on behalf of our system. It was a very weird experience because I almost felt like I was plagiarizing because people were asking me like, oh, this is a cool method. Like, why did you do X, Y, and Z? And I was like, I didn't do X, Y, and Z. Like, I made the system that made the decision to do X, Y, and Z, which I thought was really cool. And a lot of people thought it was really cool, but the general sentiment was like, when are we going to see the main conference paper? And then we had that ACL paper, which was the main conference paper. And that was kind of like, we ourselves were also like super excited and built up for that.
Yeah, it's an interesting point actually you mentioned. So like, I guess in terms of like assigning credit or taking responsibility, how do you, I guess, kind of think about that?
So I think the big thing about like that we were thinking about when it comes to like the credit of the system is it was important for us not to list the system as an author, because at the end of the day, authorship is like a responsibility, and an autonomous system like that, doesn't have like an embodiment, can't really like take responsibility like that. So at the end of the day, we wanted to make sure that, it's our responsibility to review the work, make sure it's real, submit, answer the questions that the reviewers might have, like discuss it. And, there's no real system for an AI to like take accountability on their work like that, right? So that was kind of our perspective. I think moving forward, we're not really planning to submit works to conferences, at least in that fashion. We really just want to make sure the results kind of speak for themselves, and we don't need like a academic board to validate them for them to be exciting.
Yeah.
Right? So
Makes sense.
Oh, that would have been nice.
Close. I guess.
Oh.
Go for ball in hand. I think more people will play that.
Meaning I can just place it anywhere?
Place it anywhere, hit it anywhere.
Okay, I'm just gonna hit this solid real quick.
All right.
Or not, or I won't hit it.
Right, and so everything that happened with, getting accepted in the conference and all that, I think that was now 6 months ago, which
I think so, somewhere around there.
something like that, which as we know is like a decade in AI years. So yeah, what's going on now? I know you have like the second agent. What's going on?
Yeah. So we recently released some early benchmark results of our new system we're calling Locus. I guess the kind of differences between our two systems has been our previous system was much more of a overly complicated, like multi-agent, multi-level system that had all these different parts of it, all these different aspects of the scientific method for different problems. And basically Locus is much more direct in the sense where it takes the code base, it takes the problem description that that code base is looking at, and then it takes the metrics that that code base cares about. So for example, if that code base is training a model, then the metrics could be, some sort of way to evaluate that model. If it's some kernel code, the metric would be, the end-to-end speed up of that kernel. And then it basically kicks off its research process of looking at the existing code, looking at what's out there, proposing new ideas, and then similar process of coming up with a few ideas, testing many of them in parallel, executing them all, and then kind of having this intelligent way to search as it continues to propose more and more experiments until it finds, methods or artifacts in that software that improve on those metrics better than what was given. So that's kind of the way it hones its search and kind of tries to improve the technology in this kind of research process as it operates.
Right. So I guess maybe a bit more recursive, a bit more long horizon.
Yeah. it's like, for example, in the previous agent, it had a lot of decision making on if it wanted to do more literature review or, call other tools, things like that. For this, it's like a lot of the fat is stripped down. It's much more on like, how do we propose the best experiments? And then how do we learn the right information from those experiments? And those are kind of the two things we've just focused a lot of time on, because that's kind of how we make sure the system can operate for days and continuously improve and see better results over time, rather than kind of stumbling around and maybe hill climbing on some numbers and not really making large improvements.
Right, so it's doing like thousands of experiments in parallel, plus now it's running for multiple days. Like, how do you wrap your head around, I guess, kind of like the magnitude of that? Like, what order of magnitude better is that, or more efficient would you say that is?
We ended up like benchmarking it against a variety of different benchmarks, and it got some pretty incredible results. We got state-of-the-art on Emily Bench Lite, which was pretty exciting. We got some awesome results on Kernel Bench, and then our big result that we got a lot of attention for was there's this benchmark called RE Bench that was proposed by Meter. They're like a nonprofit benchmarking organization, and they basically had a bunch of different what they called research engineering problems that could be optimizing kernels, training models, things like that. And then they had a bunch of PhD students from Berkeley and a few other places, and even some research scientists from OpenAI kind of look at these problems, given a set of GPUs, operate over the course of 64 hours, and then they benchmark their performance at each 8-hour mark and kind of show that humans can do really good over the course of a few days, and agents can only improve a certain amount and then kind of falter. And then what we were able to show was, given the same amount of time and resources as the humans, not only could our system operate for days, but it actually outperformed the baseline of the humans on the given tasks. So that was kind of a really cool result that we were able to share, and kind of gave us confidence that we're heading in the right direction, and our system can make some real serious progress on some difficult problems.
And you kind of mentioned it'll put a bit more thought into kind of topic selection. Is that, it seems like a difference between the first artificial scientist, right, where you said it kind of will take thematic areas and input. Is it now, I guess, a bit more on like the exploration side? Is that a bit an area of focus?
Yeah, I would say a lot of the research has been in kind of like this search of when do you explore, rather than when do you focus on improving certain methods, right? There's always this kind of push and pull where you want to promote the system of coming up with new ideas, but you also want it to put more effort into ideas that already seem promising. There's kind of this kind of like, and there's kind of all these underlying factors on how do you guide the search intelligently, right? Like based on previous experiments, which experiments do you look at to inform the next set? How do you define what was a good result? What was a bad result? These are all kind of questions that human researchers do when they work, right? We run some code, we learn from that code in, I guess, the ML domain, and then we kind of gain some intuition on how to continue. So we've just spent a lot of time on thinking about how do we, gain the right insight from these experiments, and how do we, see those improvements over time.
Well, you bring up code.
Yeah.
It's actually, I thought it hit a nice bank shot there. Yeah, it's actually something else I wanted to talk about was the coding domain, right? That's where we're seeing breakthroughs in kind of long horizon tasks.
Yep.
Where do you see us in terms of like reaching code AGI, and then is that translatable to, kind of scientific discovery AGI? Do they go hand in hand, or do you think they're pretty siloed?
Yeah, well, I think it's an interesting question. I mean, I think on the first question of where are we with just automating coding, we have to be pretty close. I think, if we're not at least close to being there, we will be there by the end of the year at latest. And I think, but on the topic of kind of how do these things differ, I think when we talk about the exact models under the hood that operate on these problems, like they're trained and tasked with doing kind of different things, right? With coding, the task is given a very specific description of an app or a problem or whatever you're exactly trying to see. The models are, when we talk about like coding AGI or whatever, we're meaning that given any description of an app, the system could just one-shot create it, right? And I guess for science, it's kind of the opposite, right? We don't actually know the result we're looking for, right? With coding agents, we know what success looks like. We know that if it's able to make the app that I described instantly, then it's like doing well. With science, it's more about, I have this problem. Here are the things that make me care about this problem. And I don't know what the best answer is. It's more about kind of continuously trying to find the best solution out there. So it's kind of a different task. I think coding agents getting better will make these systems better. At the end of the day, there is a part of the system that takes a description of an experiment and then implements that experiment in code to be executed and learned from. And that becoming more and more and more reliable only makes our system better, because then we can have more confidence that once the system proposes an idea, there is an implementation of that idea that is accurate and representative of what we'd like to see. So these things will make these other systems better, but I do think it's kind of a different problem. Like there's a different goal in mind when designing them.
Long shot here, I don't know.
Oh, nice.
Oh,
nice.
Put that one in the video.
Ooh. Are you going easy on me? Is that what's happening? Right
No,
now?
I'm not good enough to be going that.
Okay, I'm just making sure.
Feel a little bit better.
Oh wow, that was that was impressive actually.
Yeah, so ball in hand is nice because you literally
Yeah, just line it up.
pretty much can get a free one.
Nice.
Where do you also go from here now? Like, is it in weeks of autonomous work, months? Is it like just scaling on like the time axis?
Yeah, totally. Let me just nail this real quick. And I only came here to play pool. Anyway, yeah. So I think there's a lot of interesting like factors to think about with these kinds of systems. I think our intuition is that you can almost think about novelty as just synthesizing like many different small ideas, all in this kind of very fluid motion until the new idea you come up with is just so new and novel. But that's because it wasn't like directly correlated to one idea, but it could have been coordinated to like millions or thousands of different ideas. And I think we see that currently in our system in the sense where the kind of ideas it's proposing at the last step of iteration or like later steps of iteration are very different than the ideas proposed in the earlier steps of iteration. And we see this kind of compounding factor of like small ideas being synthesized into the next ideas. So I think when it comes to how do we make systems that make like real like scientific breakthroughs, I think it does have to do a lot with if we can make them operate longer, and if we can make them utilize more resources better, and if we can make them operate in more hard to verify domains. And what I mean by that is, like, for example, the way our system works so well right now is that when it's trying to make a better model or a better kernel or what have you, it always has a way to verify if the idea was good. But if you want to make like real progress and some crazy stuff, a lot of these domains don't have that, right? Like a good idea isn't measured by just if the number is higher compared to the previous number. So I think if we're talking, how do we get to the point where we have just, AI systems that just run for years and cure cancer and like things like that, then I think we have to, scale more. We have to use resources more, and we have to be able to operate on unverifiable rewards.
And it seems like the domain you're really putting your focus on is like AI for advancing AI research.
Yeah.
AI to design new architectures or to find like a new training breakthrough. That seems like it would lead to some kind of snowball effect is the thesis?
Yeah, exactly. I think, a lot of ML domains are verifiable like that. And we can also kind of experiment with our models and our different setups very quickly because, testing things in code is just very fast and we can iterate quickly that way. That's kind of like, the advantage of working on this versus like going directly for like material science or drugs, right? We don't have like a months-long, year-long loops to close, right? We just run code and we see if it's better. So yeah, primarily I would say, we're primarily focusing on just computational domains like, systems, computer science, machine learning. And I think obviously for that kind of dog feeding or fooding effect of maybe our system can help make our system better, right? So, yeah. Oh, wow, that was
a compilation of
me,
all your
me sinking the white. Whoa, that was really nice.
Nice.
Oh my God. Please keep all of those. Oh my God.
This is looking like the end, so if there's anything you want to plug or any last announcement, I think this would be the time now.
Is there anything I want to plug? Yeah, I think I covered everything interesting. I think this was awesome, so I had a great time.
Amazing. Well,
Yeah.
This would be super awkward now if I missed this, but
Wait, don't you have a Sprite? Don't you have one?
I guess we lost, yeah.
I win. Thank you.
Losing the first episode.
Okay.
Oh man.
Yeah.
I thought
did you do that for the timing of the
No.
video? 'Cause that would have been really good.
I fully did not. Yeah, I missed that shot.
I didn't say anything. Maybe I didn't know something.